Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to picture a UFO. Just, take a second and picture it in your mind right now.
You're probably imagining a silver saucer.
Exactly, like a saucer hovering over some deserted highway in Nevada.
Maybe some flashing neon lights, a humming tractor beam.
Yeah, the classic little green men stepping out of a ramp. But we are actually redefining that acronym today for this deep dive.
It's a phenomenal rebranding, honestly.
It really is. We are taking the idea of a UFO, stripping away all those sci-fi tropes, and replacing it with something infinitely more terrifying.
And infinitely more fascinating, too. We are trading flying saucers for ultra-fast outflows.
Ultra-fast outflows. So we aren't talking about aliens visiting Earth. We are talking about a mechanism so incomprehensibly powerful that it can literally shut down the birth of stars across an entire galaxy.
Right. It's a cosmic event that basically dictates the life and death of the universe's most massive structures.
And our destination for this exploration, the place we're looking at today, is a hyperluminous quasar sitting deep in the universe's past.
Yeah, it has this catalog designation that sounds a bit like a secret code. NESHH13.
NESHH13. It sounds like a license plate, but it's actually the key to a massive astronomical mystery.
Well, when we look at WISSH13, we're essentially looking at the cosmos as it was billions of years ago. It's during this period of extreme galactic construction.
Right, but what we find there challenges a lot of basic assumptions we have about the universe.
It really does. And
that brings us to the core mystery we are unpacking for you today. Because think about it, when you think of a supermassive black hole, the immediate image is, well, the ultimate cosmic vacuum cleaner.
An object famous for consuming absolutely everything that crosses its event horizon.
Exactly. Not even light escapes. So how does an object defined entirely by its ability to eat everything end up blasting away enough matter to shape the evolution of its host galaxy?
It's completely counterintuitive.
It is. How does the ultimate consumer become the ultimate disruptor?
That exact paradox is at the heart of modern astrophysics. We are looking at the very mechanics of cosmic regulation here. And the goal is to explore how astronomers are actually managing to decode these invisible winds.
Winds of plasma.
Yeah, winds of plasma moving at a significant fraction of the speed of light. And, what the structure of those winds tells us about the delicate balance of power in the universe.
So let's set the scene. We're looking at this hyperluminous quasar, WISSH13. And the data places it at a redshift of 3.294.
Which is a very specific, very important number.
Right. Now, for anyone listening who tracks early universe astronomy, you know that specific number drops it right smack in the middle of an era known as cosmic noon.
We are talking roughly 1.6 to 3.5 billion years after the Big Bang.
Let's pause on that redshift number for a second, because the mechanics of how we even know when this is happening is it's fascinating to me.
It really is. Redshift isn't just a distance marker on a cosmic highway. It's actually a measure of how much the universe has stretched while the light was in transit. Yeah. When the black hole at the center of WISSH13 emitted this X-ray light, those photons began a journey across the universe towards us. But the universe isn't static.
Space-time is actively expanding.
Exactly. Space-time is stretching.
So as the space between that quasar and our telescope stretches, the actual waves of light are being physically stretched out along with it.
They are. The literal wavelengths get longer.
Wow.
So if you have a highly energetic, tightly packed X-ray wave, and you stretch it out over a journey of 10 billion years, its wavelength shifts toward the red end of the electromagnetic spectrum.
Yin's redshift.
Right. A redshift of 3.294 means the universe has expanded by more than a factor of 4 since that light left the quasar.
That's almost hard to wrap your head around.
It is. So we aren't just looking far away. We're looking at an incredibly specific, chaotic epoch in the history of everything.
Cosmic noon. I always think of that era as like the roaring 20s of the cosmos.
That's a really apt description. If you map out the star formation history of the universe, cosmic noon is the absolute peak.
Everyone was partying.
Basically, yeah. Galaxies were colliding constantly. Colossal reservoirs of cold gas were flowing along these giant cosmic filaments.
And at the centers of these developing galaxies, supermassive black holes were feasting.
gorging themselves, really. The environment was dense and incredibly violent.
And the black hole at the center of Tulio SSH13 is a monster, even by those standards.
Oh, absolutely.
We are talking about a central mass of roughly 2 billion solar masses. 2 billion.
2 billion times the weight of our sun.
And because we are in cosmic noon, surrounded by all this raw material, this specific black hole is feeding at an exceptional rate.
But here's where the mechanics of black holes always trip people up a little bit.
Right, because we talk about a black hole feeding, but observationally what we actually see is it's shining.
Exactly.
And Wiki SSH13 isn't just shining, it is shining about 3 times brighter than astronomers would normally expect for a black hole of this staggering size.
Which forces us to look really closely at the physics of the accretion disk.
The disk of material swirling around it.
Right. The black hole itself, the singularity past the event horizon, emits no light. It's invisible.
Black.
Yes. But the environment immediately surrounding it is the brightest continuous light source in the universe.
Because when a black hole's gravity pulls in massive amounts of gas and dust, that material doesn't just fall straight down, does it?
No, it has angular momentum.
Like water circling a drain.
Exactly. It's swirling inward, forming a flattened disk, but it's not a gentle swirl.
Right.
The material in the inner regions of that accretion disk is orbiting much, much faster than the material on the outer edges.
Because it's closer to the gravity source.
Right, and this differential rotation creates immense friction. You have billions of tons of gas crowding together, shearing against itself.
Wow.
And it's moving at speeds approaching the speed of light.
And friction generates heat. But we aren't talking about rubbing your hands together on a cold day.
Not at all.
We are talking about thermal energy so intense that it literally breaks the bonds of atoms.
The temperatures soar into the millions, even tens of millions of degrees.
That's unimaginable.
It is. The gas is completely ionized into a plasma. And that superheated plasma radiates intense energy, predominantly in X-rays and ultraviolet light.
Okay, so when we measure the luminosity of WISS-13, we are basically measuring this frantic, superheated traffic jam of matter.
Exactly. Matter desperately trying to squeeze through the bottleneck of the event horizon.
It's like a messy eater at a buffet, trying to shove so much food in their mouth that it's just flying everywhere, generating all this energy just outside the event horizon.
That's a great way to picture it.
But wait, if this supermassive black hole has 2 billion solar masses, its gravitational pull is almost unfathomable.
Right.
And it's surrounded by this all-you-can-eat buffet of galactic gas. If its gravity is that strong, why doesn't it just swallow the entire host galaxy?
That's the big question.
What stops this from turning into a runaway scenario where the black hole just consumes everything until there's nothing left but the black hole itself?
Well, that very question plagued theoretical physicists for years. Yeah. If you just run the raw math on gravity and gas density in the early universe, galaxies should have grown much larger than they actually are.
Because there was so much material.
Exactly. And black holes should have eaten vastly more material. There had to be a mechanism that halted the growth.
Something that chokes off the food supply.
Right. And that brings us back to the ultra-fast outflows. The UFOs.
The universe's thermostat.
Exactly.
Okay, let's look at how this thermostat actually functions for you listening, because the survival of the entire galaxy depends on it. How does blowing gas away act as a regulatory system?
It relies on a critical feedback loop, and it all comes down to the thermal state of the galaxy's gas.
To temperature.
Right. To build a galaxy, you need to form stars. To form a star, you need a massive, dense cloud of molecular gas.
Okay.
But here is the absolute strictest rule of star formation. That gas must be incredibly cold.
This is one of those rules that feels so counterintuitive. We associate stars with immense heat and fusion, but their actual birth requires freezing temperatures.
Yes, and that's because of the constant battle between gravity and thermal pressure.
Right.
If a cloud of gas is hot, the individual particles are highly energetic. They are vibrating, colliding, pushing outward.
Like steam expanding.
Exactly. That outward thermal pressure easily overpowers the inward pull of gravity. The cloud simply expands and dissipates. It won't collapse.
So gravity needs an unfair advantage to win.
Precisely. The gas must cool down to just a few degrees above absolute zero.
Which is freezing.
Beyond freezing. And when the gas is that sluggish, the thermal pressure drops to near zero.
And gravity takes over.
Right. Gravity takes over, pulling the cloud together until the core becomes dense enough to ignite nuclear fusion.
So cold gas equals star formation.
And hot gas equals a dead galaxy.
Wow. Okay, now let's introduce the black hole's killer wind, the UFO.
So the black hole is gorging itself, the accretion disk is blazing hot, and the intense radiation pressure and magnetic fields generated in that disk actually start driving material outward.
It's like the black hole is feeding so aggressively that it pushes its own food away.
Exactly. And when these winds achieve velocities exceeding 10% of the speed of light, they become ultra-fast outflows.
And these winds aren't just empty space, right? They carry unimaginably huge amounts of kinetic energy.
Immense kinetic energy. When a wind moving at a fraction of light speed slams into the surrounding ambient gas of the host galaxy, the collision is catastrophic.
I can imagine.
It creates massive shock waves. It acts like a cosmic blowtorch, transferring all that kinetic energy into thermal energy.
Oh, I see. So the ambient gas in the galaxy is suddenly heated up to millions of degrees.
Right. And because the gas is now superheated, the thermal pressure spikes.
And gravity loses the battle.
Exactly. The gas can't collapse into molecular clouds, which means it can't form stars.
So the UFO effectively quenches the galaxy.
It does. If the wind is powerful enough and sustained over a long enough period, it will either heat the gas so thoroughly that star formation permanently shuts down, or it will literally sweep the gas entirely out of the galaxy's gravitational well, just blowing it into intergalactic space.
Just emptying the cupboards. Think about the philosophical implication of that for a second.
The deep.
If you are listening to this, you likely grew up learning that black holes are the ultimate symbol of destruction.
The great erasers of the universe.
Right. They are the void that crushes matter out of existence. But functionally, within the mechanics of a galaxy, the black hole is the regulator.
It is.
It dictates the life cycle of stars. It regulates its own massive growth by violently blowing its food source away. And in doing so, it freezes the host galaxy's ability to grow any further.
It's an incredibly elegant, albeit violent, symmetry.
Elegantly violent, I like that.
Because without these relativistic winds, galaxies during cosmic noon might have just converted all their available gas into stars in one massive, uncontrolled burst.
And black holes would have swelled to impossible proportions.
Right. The universe would look fundamentally different today.
So it really is a thermostat. The galaxy gets too hot, meaning the central black hole is feeding too rapidly, and the system triggers a cooling mechanism.
Yeah.
Except the cooling mechanism is a lethal gale of highly ionized plasma that shuts down the factory entirely.
A self-correcting system operating on a scale of hundreds of thousands of light years.
Okay, the mechanical logic of the thermostat makes perfect sense. The black hole eats, the disk gets chaotic, radiation pressure drives the winds outward, the kinetic energy shocks the host galaxy's gas, it heats up, star formation dies.
That's the sequence.
But here is where my mind starts to bend, and I know anyone listening who understands the vastness of space is probably wondering the exact same thing.
How do we actually see it?
Yes, WISS H13 is at redshift 3.294. We're looking across billions of light years of empty space to see a wind made of transparent gas. How on earth do you observe an invisible wind moving away from a tiny pinprick of light from the dawn of the universe?
That observational challenge is, it's immense.
It sounds impossible.
Historically, if astronomers wanted to study anything in that level of detail at high redshift, they had to rely on a phenomenon called gravitational lensing.
Ah, gravitational lensing. That's one of those concepts that feels like magic but is just pure, unadulterated general relativity.
Exactly. General relativity tells us that massive objects warp the actual fabric of space-time around them.
Like a bowling ball on a trampoline.
Right. So imagine YSH13 sitting out in the distant universe, pumping out its light. Now imagine there happens to be another massive galaxy sitting directly in the line of sight between Earth and YSH13.
A foreground object.
Yes. As the light from YSH13 travels toward us, it encounters the warped space-time created by the gravity of that foreground galaxy.
Okay.
The light follows the curvature of space, bending around the foreground object.
So the gravity of the foreground galaxy acts exactly like a giant glass lens.
It does. It focuses the distant light, magnifying the background quasar, making it appear significantly brighter and larger than its intrinsic luminosity.
So if you're trying to measure something incredibly faint and difficult to resolve, like a wind of plasma rushing off an accretion disk, a cosmic magnifying glass sounds like the perfect tool.
You would think so.
Right. Why wouldn't astronomers just use lensed quasars to study UFOs?
Because a gravitational lens is not a perfectly ground, pristine optical lens manufactured in a clean room laboratory.
Oh, right.
It is a messy, chaotic galaxy. It is composed of billions of stars, vast clouds of swirling gas, and complex halos of invisible dark matter.
So the lens itself is full of smudges and structural flaws.
That's a really great way to think of it. When you bend light through a galaxy's gravity, you inevitably distort the data.
Because it's uneven.
Exactly. The magnification is rarely uniform across the entire image. The lens can create multiple, distorted, mirrored images of the exact same background quasar.
Like a funhouse mirror.
Exactly like that. Furthermore, individual stars within the foreground galaxy can cause microlensing events.
What does that do?
Those temporarily spike the brightness of specific regions of the accretion disk, throwing off all the calculations.
Wow.
So if your goal is to precisely measure the velocity, the structure, and the mass of a wind launching off the innermost stable circular orbit of a black hole.
Which requires insane precision.
Right. The distortions introduced by the lens can easily trick you. You might vastly overestimate the power of the wind or misinterpret its geometry entirely.
So if we can't use a magnifying glass because it smears the image and corrupts the data, how are astronomers actually getting a clean look at these systems?
That exact problem led a team of researchers, specifically spearheaded by Giorgio Lanzuzzi at INEF Bologna, to launch a highly ambitious observational campaign called the Wish-Medal program.
The Wish-Will program. And their strategy was basically to do this the hard way.
Precisely. It is a multi-year heritage program utilizing the XMM Newton Space Observatory.
Okay.
Their goal was to target 15 hyperluminous, completely non-lensed quasars at cosmic noon.
And WISH SSH-13 was the very first target in this campaign.
Yes. They decided to forego the magnification boost entirely. Instead, they relied purely on the extreme intrinsic brightness of these specific quasars, combined with long, incredibly patient observations using our most sensitive X-ray detectors.
This requires a massive amount of telescope time, right?
Hundreds of hours.
They point the XMM Newton, and eventually they pull in the Nustar telescope as well at this tiny, unmagnified pinprick of X-ray light.
Right?
But if they aren't using a lens to physically resolve the shape of the wind, what is the telescope actually recording?
Yeah.
We aren't just taking a long exposure photograph, right?
No, a photograph wouldn't tell us anything about the velocity or the composition of the gas.
Right.
To decode a UFO, you have to take a spectrum. You have to read the cosmic fingerprints.
If you are listening to this and wondering how we know what stars are made of or how fast galaxies are moving across the universe, spectroscopy is the answer.
It is the absolute heavy lifter of astrophysics.
It really is.
Yeah.
But let's dive into X-ray spectroscopy specifically because the mechanics here are wild.
They really are. At its core, a spectrum is a barcode of light.
A barcode.
Right. If you pass visible white light through a glass prism, it disperses into a continuous rainbow.
Like Pink Floyd's Dark Side of the Moon cover.
Exactly. X-ray spectroscopy does the exact same thing, just at vastly higher energy levels.
Okay.
The superheated accretion disk around WISH-13 is acting like a cosmic light bulb, pumping out a smooth, continuous continuum of X-ray energies.
A blazing rainbow of lethal radiation.
But between that brilliantly glowing disk and the XMM Newton telescope orbiting Earth, there is the wind.
The ultra-fast outflow.
Yes. This wind is composed of plasma. As the X-rays from the disk travel outward, they must pass through this outflowing wind.
And when they do, the atoms in the wind interact with the light.
They do. Specifically, they absorb very specific, highly targeted energies of X-rays.
So when the light finally arrives at our detectors here on Earth, the continuum isn't smooth anymore. The barcode is missing specific lines.
We call these missing lines absorption features, or absorption troughs. The specific energy that is subtracted from the spectrum tells us exactly what elements the wind is composed of.
Because every element has a unique signature.
It's a fundamental rule of quantum mechanics. Every element on the periodic table absorbs a unique, irrefutable signature of light based on its electron configuration.
Okay, but if you're listening to this and trying to picture the environment right next to a supermassive black hole, you might see a flaw in that logic.
Oh!
Yeah. The accretion disk is generating tens of millions of degrees of heat. It is blasting out enough X-ray radiation to outshine an entire galaxy.
True.
Wouldn't normal atoms just be completely vaporized? How does an atom hold onto its structure tightly enough to absorb a specific wavelength of light without just being ripped to shreds by the radiation?
That is a brilliant point, and it's the key to why X-ray spectroscopy is so vital here.
Because normal atoms wouldn't survive.
You are right. Normal, neutral atoms cannot survive in that inferno. The radiation completely strips their electrons away, turning them into a featureless soup of protons and electrons.
And a featureless soup doesn't leave clear spectral lines.
Exactly. But there is one very specific element we look for that can survive.
Iron.
Iron.
But not normal iron. We are talking about highly ionized iron.
Yes. Iron is a relatively heavy element. Its nucleus has a strong positive charge.
So it holds on tight.
Right. In the extreme environment near the black hole, the intense heat and radiation violently strip away almost all of the iron atom's electrons.
Almost all.
But the innermost electrons, the ones closest to the nucleus in what we call the K-shell, are bound so tightly that they manage to survive the inferno.
Wow.
We are looking for iron atoms that have been stripped of 24 or even 25 of their 26 electrons.
So it's basically just a naked iron nucleus holding on to its last 1 or 2 electrons for dear life.
Exactly. Astronomers refer to these as helium-like or hydrogen-like iron.
Because they only have 2 or 1 electron left, mimicking the structure of those lighter elements.
You got it. And when an X-ray photon of the exact right energy hits one of those highly ionized iron atoms, the remaining electron absorbs the photon and jumps to a higher energy state,
leaving a gap in the light.
This leaves a massive, unmistakable dip in the X-ray spectrum at a very specific energy level, typically around 6.7 to 6.9 kilo-electron volts in a laboratory setting.
So Giorgio Lanzvisi's team looks at the new XMM Newton data from October 2024. They combine it with archival data from 2017 to boost the signal-to-noise ratio, and they look at the spectrum.
And they find it.
They see the unmistakable missing iron barcode. They have absolute proof that a cloud of highly ionized iron plasma is sitting between us and the black hole.
But proving the gas is there is only half the battle.
Right. How do they know it's a win? How do they prove it's actively moving?
Because the barcode is in the wrong place.
The wrong.
It's shifted. To understand why, we have to look at the Doppler effect.
You know how the textbook analogy for the Doppler effect is always the ambulance siren?
Yeah, driving past you.
Let's ditch that, because we're talking about relativistic speeds in a cosmic hurricane. Imagine you were driving your car down a highway directly into a massive, heavy rainstorm.
Okay, I like where this is going.
If you are parked, the rain is hitting your windshield at a steady, consistent rate.
Right.
But if you slam on the gas and drive at 100 miles an hour directly into the storm, the rain starts hitting your windshield much faster and much harder.
Because you're moving into it.
The frequency of the impacts increases dramatically simply because of your forward motion into the rain.
That is an excellent way to visualize it. The light waves from the accretion disk are the rain.
Okay.
If the iron gas in the UFO was just sitting still, hovering above the disk, it would absorb the X-rays at the standard expected energy.
That 6.7 kilo-electron volt mark you mentioned.
Exactly. But the iron gas isn't sitting still.
Right.
It is rocketing away from the black hole directly toward Earth at a massive fraction of the speed of light. It is driving directly into the incoming X-ray photons.
Driving into the rainstorm.
Therefore, from the perspective of the moving iron atoms, the incoming X-ray waves are compressed.
Because they're slamming into them.
The impacts are happening at a higher frequency. The light is shifted toward the blue end of the spectrum, meaning it shifts to a higher energy state.
This is blue shift.
This is blue shift.
So when the astronomers look at the spectrum, the iron absorption dip isn't at 6.7. It's pushed way up the energy scale.
Precisely. And the amount of that blue shift is governed by strict mathematical laws.
Right.
By measuring exactly how far the barcode has shifted up the energy scale, astronomers can calculate the exact velocity of the gas. The spectrum acts as a cosmic radar gun.
The precision of that is staggering. You look at a missing line of light, measure how far off center it is, and suddenly you know the speed of a wind located billions of light years away.
It's one of the great triumphs of astrophysics.
So what did the radar gun say? How fast is the killer wind in WISS 13 actually moving?
This is where the discovery elevated from an interesting observation to a truly groundbreaking find. When the team ran the spectral modeling to fit the data, they didn't just find one blue-shifted trough.
Wait.
The data clearly revealed two distinct absorption features. They found two completely different speeds originating from the same system.
Wait, two speeds? A dual-velocity wind from a single black hole?
Yes. The sophisticated modeling of the X-ray spectrum isolated two distinct velocity components of the exact same ultrafast outflow.
Okay, so what are the speeds?
One component of the wind is traveling at roughly 10% the speed of light, about 0.1 c.
Just to anchor that for a second.
Yeah.
10% the speed of light is about 30,000 kilometers per second.
Right.
You could travel from New York to Tokyo in less than half a second. That speed alone is cataclysmic.
It is a phenomenal velocity, but the second absorption component they isolated is traveling at approximately 30% the speed of light.
30%.
0.3c.
90,000 kilometers per second.
Yeah.
There is no earthly analogy that can adequately convey that kind of kinetic energy. It is terrifying speed.
Yeah. It is. But what makes this system even more fascinating is when the team cross-referenced the temporal data.
Temporal meaning the timing of the observations.
Right. Remember, they have two sets of observations. The older archival data from 2017 and the fresh data from October 2024.
Right. So what changes over 7 years?
The slower wind, the component moving at 10% the speed of light, was clearly present in both the 2017 data and the 2024 data.
So it's always there.
That consistency tells us it is a persistent, long-lived feature of the accretion system. It's a steady, unrelenting gale.
Okay, but what about the faster wind?
The faster wind, the one rocketing outward at 30% the speed of light, only appeared in the 2024 data.
Really?
Its signature was completely absent in 2017.
So it just turned on.
It indicates that this extreme high-velocity wind is not persistent. It is launched in volatile, short-lived episodes.
It's a gust.
Right, flares up dramatically and then shuts down or dissipates. And when you analyze these two pieces of evidence together, a steady, slower wind accompanied by an episodic, volatile, faster wind, it provides spectacular observational support for theoretical models.
Models of what?
What we call a stratified outflow.
A stratified outflow, a layered wind.
Yes, a wind that possesses a distinct, complex anatomical structure. Astronomers often describe it as having a spine and a sheath.
A spine and a sheath. I'll make sure I'm visualizing the geometry of this correctly.
Okay.
Think of a wildly rushing river, or even the exhaust of a high-performance jet engine. If you look at a fast-moving river, the water right in the dead center, the deepest channel, moves violently and incredibly quickly. It's chaotic.
That's the spine.
But the water closer to the riverbanks, where there's more drag and less direct pressure, moves slower and much more consistently. That's the sheath.
That analogy maps remarkably well to the physics of the accretion disk. Yeah. The geometry of the black hole's wind operates on very similar principles, although it is governed by extreme gravity and twisted magnetic fields rather than riverbanks.
Sure.
The spine of the wind, that episodic component moving at 30% light speed, is launched from the innermost, most extreme regions of the accretion disk.
Right on the precipice of the event horizon, the deepest part of the gravitational river.
The region known as the ISCO, the innermost stable circular orbit.
ISCO.
The gravitational and magnetic forces there are at their absolute maximum, which provides the immense energy required to propel the plasma to such terrifying velocities.
But because it's so extreme, it's unstable.
Exactly. Because that inner region is so tightly packed, radiation-dominated, and chaotic, the launching mechanism is inherently unstable. It builds up pressure, bursts outward in an extreme episode, and then temporarily exhausts itself.
Which perfectly explains why the telescope only caught it in the 2024 observation.
Exactly. Meanwhile, the sheath component moving at 10% light speed originates further out on the accretion disk.
Where things are slightly calmer.
Right. The gravitational and radiation forces there are still immense, easily powerful enough to drive a relativistic wind, but the environment is wider and slightly less extreme,
making it more reliable.
This allows for a more stable launching mechanism, creating a steadier, more persistent outer layer of the outflow.
That structural reality is what truly blows my mind. When you initially think of a black hole blasting out gas, you picture an explosion.
Like a bomb.
Right, a chaotic spherical bomb going off. But it's not a bomb. It's highly organized.
It is.
It is a structured, multi-lane highway of plasma, where the fast lane is flashing on and off with explosive violence, and the slower lanes maintain a steady, unrelenting storm.
The term organized chaos has never been more appropriate.
Yeah.
The sheer physical forces required to maintain a stratified wind structure moving at relativistic speeds, fighting against the gravity of a 2 billion solar mass black hole, is staggering to contemplate.
So understanding this layered structure paints an incredible vivid picture of the immediate environment just outside the event horizon.
It does.
But to bring this back to the big picture, to truly understand how this wind acts as the cosmic thermostat that regulates the galaxy, we have to look at the volume.
The mass.
Right, velocity is one variable, but how much physical matter is actually being hurled out into the host galaxy?
The mass ejection rate is where the true catastrophic scale of this phenomenon hits you.
Hit me.
By analyzing the depth of the absorption troughs, estimating the density of the plasma, and calculating its distance from the ionizing source, the team was able to determine the mass outflow rate.
They calculated how much stuff is blowing away.
They calculated the amount of material being expelled by these two components combined.
That's the number.
Together, the spine and the sheath are ejecting a combined total of roughly 45 solar masses of material every single year.
Wait, 45?
Specifically, it breaks down to about 21 solar masses per year from one velocity component and 24 from the other.
45 solar masses a year. Let's really lean into that.
It's huge.
We were used to talking about solar masses when we were weighing static objects. A star cluster is 100 solar masses. A black hole is 1 billion solar masses. But seeing that number as a flow rate, as an ejection rate, that's terrifying.
Yeah?
Every single atom of hydrogen and helium that makes up our million-mile-wide sun, that is 1 solar mass.
Now multiply that by 45 and set the time frame to a single Earth year.
It's like imagining a cosmic cannon loading up our entire sun and firing it out into the void at up to 30% the speed of light.
Just boom.
And then reloading and firing it 44 more times before the year is out.
The sheer kinetic energy carried by that volume of mass moving at those speeds makes the UFO in YOSSH-13 one of the most massive and powerful ever discovered.
Unbelievable.
And because it was identified without the aid of a gravitational lens, the data is exceptionally clean.
Right. No smudged magnifying glass.
It currently stands as the highest redshift UFO detected from a non-lensed quasar. It gives us a pristine, uncorrupted look at a galactic monster operating at the absolute peak of its power during cosmic noon.
But here is where the story gets really interesting for me, and it touches on something deeply fundamental about how the universe works.
The scaling relations.
Yes. You have this massive, chaotic system in the early universe throwing out 45 suns a year. Yet the observations found that these winds follow the exact same scaling relations observed in active galaxies that are much closer to us in the modern universe.
Yes, and from a physics standpoint, that might be the most profound takeaway of the entire observation.
Really?
In astrophysics, we rely heavily on scaling relations. These are empirical, mathematical relationships that describe how different properties of a system correlate with one another across different scales.
There are rules to how these things operate.
Exactly. For instance, in the local modern universe, which we observe at low redshifts, astronomers have established a strict mathematical relationship between the kinetic power of black hole's wind and the mass and total luminosity of the black hole driving it.
There is a predictable universal rulebook for how black hole feedback operates.
If the black hole weighs X and shines at Y, the wind will have Z amount of kinetic power.
Got it.
Now, if you consider the environment of the early universe during cosmic noon, it was wildly different than the local universe today.
Oh, right, because everything was denser.
The gas density was far higher, galaxies were physically smaller and closer together, mergers were constant, the raw material available for accretion was vastly more plentiful.
It was the roaring 20s.
Exactly. You might reasonably expect the physics of accretion and wind launching to behave differently in such an extreme, chaotic epoch.
Right. If I can use a biology analogy here, finding that these scaling relations hold true at redshift 3.294 is like a paleontologist digging up a massive, terrifying 10-foot-tall dinosaur from a completely different era of Earth's history.
Okay.
And discovering that its metabolic rate, its blood pressure, and its cellular biology follow the exact same mathematical rules as a modern pigeon walking around Central Park.
That perfectly captures the revelation. The environment is drastically different, the epoch is billions of years in the past, the sheer scale of the energy output is magnitudes higher, but the fundamental physics, the underlying engine driving the phenomenon, has not changed.
It's the same engine.
The rules of physics governing how supermassive black holes regulate their environments have remained firmly intact for over 10 billion years.
That is deeply comforting in a weird way.
Comforting.
Yeah. As violent and chaotic as the universe appears, the underlying math holds firm. The laws of nature are consistent.
They are very consistent.
So knowing that these universal rules apply, even to the most extreme monsters at the dawn of time, and knowing that we can successfully measure them without relying on gravitational lenses, where do astronomers go from here?
Well, the successful observation of WSSH-13 is a powerful proof of concept.
It shows we can do it.
It proves that we have the methodology to decode these high redshift systems cleanly. Looking to the future, the astrophysics community is incredibly focused on the next generation of space telescopes.
Like what?
Specifically, the planned New Athena X-ray Observatory.
Tell me about New Athena. How does it improve on what XMM Newton is already doing?
New Athena is designed to be a massive leap forward in both collecting area and spectral resolution.
It's just a bigger, better eye.
Essentially, it will utilize advanced microcalorimeters that can measure the energy of incoming X-ray photons with unprecedented precision.
So the barcode gets clearer.
Exactly. If XMM Newton allowed us to detect the broad dips of the iron absorption trough, New Athena will allow us to see the fine structure within that trough. It is specifically designed to identify and characterize these winds in distant quasars at a much faster rate.
That's exciting.
If the Wish-Wolf-Fuel program and WISH-13 represent the artisanal, painstaking proof of concept, New Athena will be the factory.
Just churning out data.
It will allow us to map out the cosmic thermostat across hundreds or thousands of galaxies during cosmic noon.
Which opens up an entirely new era of understanding how the universe evolved from a chaotic soup of gas into the structured, stable galaxies we see today.
It really does.
Let's synthesize this journey for you listening. We started by looking at a supermassive black hole, an object defined in the public consciousness by its voracious appetite and inescapable gravity.
The vacuum cleaner.
Right. But what the data shows us is that black holes are not just cosmic vacuum cleaners. Because they eat so aggressively, because the differential rotation in their accretion disks generates such blinding millions of degrees heat, they actually create these stratified multi-lane highways of highly ionized iron plasma.
The ultra-fast outflows. Layered winds moving at 10% and 30% the speed of light.
Right. And these winds carry so much mass firing, 45 suns worth of material a year into deep space, and so much immense kinetic energy that they violently shock and heat up the ambient gas of the entire host galaxy.
They strip away the cold gas supply necessary to make new stars.
They act as the ultimate cosmic thermostats, dictating whether a host galaxy thrives and continues to grow or is violently quenched and left to slowly fade.
The ultimate destroyer is functionally the galaxy's regulator.
It is the essential feedback loop that shapes the entire cosmos.
Without it, we wouldn't be here.
And that leaves us with a final thought to mull over, something that builds on the mechanics we've explored today.
Okay.
If you're listening to this, you're currently located in the Milky Way, a stable, beautiful spiral galaxy.
Our home.
But if supermassive black holes inherently limit the size and star-making ability of their host galaxies by literally blowing the building materials away, does this mean the universe has a strict, mathematically enforced, maximum size limit for any civilization's home galaxy?
That is a fascinating extrapolation of the thermostat model.
Think about it. We look up at the night sky and see a galaxy that had been stable for billions of years. But are we only living in a stable environment because long ago the supermassive black hole at the center of the Milky Way woke up, lashed out, and violently blew away the excess gas before the galaxy could tear itself apart with uncontrolled massive starbursts?
It's very possible.
Are we living in a cosmos where nature's ultimate destructive force, a mechanism that can hurl 45 suns a year at relativistic speeds, is the exact and perhaps only reason our galaxy is stable enough for biological life to exist at all?
It is a profound realization. The extreme violence that prevents a galaxy from growing infinitely is likely the exact regulatory mechanism that ensures its long-term survival and stability.
The ultimate destroyer, acting as the ultimate preserver, a cosmic thermostat keeping the house just stable enough for us to live in it.
That's beautifully put.
Just something to think about the next time you look up at the night sky.